Bem-vindos ao nosso espaço, um mergulho profundo nos assuntos mais interessantes de esportes, ciências e temas gerais do momento. Aqui você vai encontrar conteúdo de qualidade, com análises empolgantes e descobertas fascinantes que vão expandir seus horizontes. Nossa missão é trazer informação relevante de forma dinâmica e descontraída. Queremos que você faça parte dessa jornada incrível de conhecimento e diversão. Se gostar do nosso conteúdo, não esqueça de deixar seu like e se inscrever no canal para não perder nenhuma novidade. Ative o sininho também. Aproveite!
If you love science, don't forget to like and subscribe. Imagine two particles, linked regardless of the distance separating them. Change the state of one, and the other instantly responds. This is quantum entanglement, famously dubbed spooky action at a distance by Albert Einstein. It is the cornerstone of quantum computing and communication, promising speeds that transcend our current understanding of physics. But entanglement is fragile. It is constantly battling decoherence, the loss of its quantum state due to interaction with the environment. Normally, this process takes time, sometimes microseconds, sometimes longer. However, a fascinating hypothesis suggests that certain rare minerals possess an internal structure so unique and hostile to quantum coherence that they act as a chronometric filter, destroying entanglement almost instantaneously. The term chronometric relates specifically to the measurement or analysis of time. When we discuss a chronometric filter in this context, we are talking about a material that doesn't just block a signal. It fundamentally accelerates the local passage of interaction that leads to quantum state collapse. To understand why this happens, we have to look inside the atomic lattice of these materials. Most materials cause decoherence by providing loose, random interactions, a stray electron here, a thermal vibration there. But a few select minerals, notably certain isotopes of zircon, beryl, and even highly purified dense oxides, exhibit crystalline structures that are rigid, highly symmetrical, and extraordinarily dense. The structure of, say, high-density zircon, zirconium silicate, is almost architecturally perfect. Its atoms are locked into fixed positions, creating a predictable, repeating, and extremely stable energetic environment. This isn't a chaotic environment, it's an overly ordered one. And in the bizarre world of quantum mechanics, excessive order can be just as destructive as chaos. When entangled quantum systems, perhaps photons or electrons, pass through or interact with this perfect lattice, they are not just bumped by random noise. Instead, they are subjected to an immediate, powerful, and uniform interaction with the material's internal fields. This interaction is mediated by phonons, quantized units of vibrational energy that travel through the crystal lattice. In standard materials, phonons might be scattered or diffuse. In a chronometric filter mineral, the phonons travel in highly predictable, tightly packed waves. These waves act like an internal, hyperfast time signal, forcing the entangled particles to interact simultaneously across multiple, perfectly positioned atomic centers. The key is the speed and uniformity of this interaction. Instead of the gentle, staggered environmental interaction that allows entanglement to persist momentarily, the filter delivers a massive, coordinated temporal jolt. Think of it this way. Entanglement is like two perfectly tuned pendulums swinging in sync. Decoherence is when a breeze or vibration slowly knocks them out of phase. The chronometric filter isn't a breeze. It's a perfectly timed sonic boom delivered simultaneously to both pendulums by the material itself. Because the energetic interaction, the jolt, is so quick and spatially consistent across the material, the time available for the quantum state to maintain its coherence is drastically reduced, often to picoseconds or less. It's like the material has locally sped up the time of decoherence. This phenomenon has profound implications, particularly for quantum cryptography and the burgeoning field of quantum networks. While scientists are desperately searching for materials that preserve entanglement, understanding these chronometric filters allows us to define the absolute physical limits of quantum communication channels. If we can map the precise isotopic or structural factors that cause this instant collapse, we gain valuable insight into the fundamental vulnerabilities of quantum information. For example, studying minerals that exhibit this filter effect helps researchers design protective casings and insulators for quantum processors, ensuring that environmental factors, even the structure of the surrounding material, do not prematurely collapse the qubits. Conversely, these filters could become essential tools in future quantum devices, acting as internal reset switches or physical barriers to isolate delicate quantum circuits from each other. The chronometric filter is not science fiction. It is the cutting edge of material physics, showing us that the internal structure of common geological components can dictate the behavior of subatomic particles across space and time. It confirms that the environment isn't just a background player, it is an active participant in defining the reality of quantum mechanics. For more incredible facts like this, don't forget to subscribe and turn on notifications.